Hello.
Yeah, Mangesh, yes.
Yeah,
Yeah, you can go ahead.
correct. I'm just sharing my screen. Let me know once it's visible.
Yeah. Yeah, I can see
Oh,
your screen.
thank you, Ali, for the introduction and confirming this. So I hope all are able to see my screen and are able to hear me clearly. So welcome all to the today's session on in silico modeling of the patient-specific heart. Myself, Mangesh, application engineer at CADFAM. So today I'll be taking you through this particular session where we'll be discussing about how in silico modeling is being utilized for the patient-specific heart modeling, some examples of or the case studies where heart modeling has been deployed and been utilized effectively. What all different simulations are being conducted for heart surgeries, right? So those are the maybe cases or examples which we'll be looking through this particular session. Before diving into that, again, I'll be just going through a couple of slides where we'll be introducing what is computational fluid dynamics. Probably, if you have already attended the previous session for the bioreactors or the mixers, you might have already seen these slides, but for the attendees who are new to this, maybe for them could be useful. So, what is computational fluid dynamics? So, it's a science of predicting fluid flow, heat, and mass transfer, and chemical reaction related phenomena. Let's say fluid dynamics is all what deals with the flow of any fluid, the interaction of it in the form of heat and mass transfer, and the interaction of the fluid in the form of chemical reaction. So, when we try to model it using some numerical methods, model it and try to perform these analysis using computational option or computational resource. That's where we call it as computational fluid dynamics. So again, a brief about this different. Okay, I just maybe someone might have requested for request. I guess it won't be the close this. Yeah, so just a again a brief about these different um, uh, topics, let's say in vivo, in vitro, and in silico. So in vivo is all about you know the kind of analysis which is happening within the living organisms, right? Like surgery or any kind of reactions which are happening, and if the study is intended in that direction, then it's called an in vivo study. Whenever the study is being conducted or the analysis is being conducted on the exterior or the external side of the living organ, so that we would call it as an in vitro kind of analysis. And when such analysis are performed using some kind of a computational option like computational fluid dynamics, where we are using the silicon chips for solving equations and then eventually identifying the performance of this um, human organs. So that's where we call them as in silico. So of course, in earlier days, in vivo, in vitro used to be mostly been considered, but nowadays with the advancement of simulation, the simulation can be very effectively used to identify the performance of such human organs as well, model them, even if they are complicated. Definitely, they are complicated. We'll be seeing in the coming slides. But yeah, still, because of the advancement, the developed models, the developed strategies of analysis, these days we will be, we are able to very effectively perform simulations. A brief about what is CFD and what all you can collect out of CFD and what are the different stages where CFD is being used. So yes, it's a science of collecting fluid flow, heat, and mass transfer, and there are certain equations, conservation equations, uh, conservation of mass, momentum, energy equations, which are getting solved in the background, and depending on the kind of physics we are trying to solve, these number of equations and the kind of boundary conditions or the informations which we have to input changes, and depending on the kind of information we are looking for, we can decide upon the kind of simulation to go for. And the very generic informations we can extract would be like the overall pressure drop across systems, like let's say consider a heart, right? It's a if you look at as a from a layman term, it is simply a pump. So it is supposed to pump some fluid. So during this pumping action, it might have to work against some pressure drop. So that's how one might be looking into like what is the overall pressure drop created by this pump, what is the flow rate, velocities, okay. Yeah, in some cases maybe temperature as well. So these are, let's say, some outputs or informations one might look for when they relate it to the hard simulations. Of course, one can relate it to other simulations for the in silico approaches as well. Apart from that, other details could be like, forces on the arteries, right? Forces or the pressures on the different devices which we have to, put up as an implants, or let's say take an example of a stent in a artery. So what are the forces, fluid forces acting on those components, and then what would be the life of those components after continuously uh, getting exposed to such forces. Then distribution of the phases, if in case it's a multi-phase case, species compositions. So yeah, there are multiple details one can extract. Apart from them, the different stages where we can use such analysis. So you can see we can use this tool for conceptual level understanding. Let's say if you are developing any drug delivery product or a implant, then maybe you might come up with different concepts, and then testing these concepts on the actual patients would be a really tedious task. That's where this virtual environment can help them. Yeah, beyond that, the detailed analysis or improving the product. So in the couple coming slides, we will be discussing on the optimization part, which again would be very complicated to do on an actual patient. Shooting, if in case some implant is having some issue, then troubleshooting that or redesigning. So these are some of the stages where we can utilize this CFD tool very effectively. Happening in the background, well, within CFD, the actual domain of interest, let's say in this case, you see a pipe is being discretized into small control volumes, and the equations, the ones which I mentioned previously, like the conservation of mass, momentum, and energy, or depending on the kind of physics you are applying, the equations might add up. So those conservation equations are solved for such control volumes, and that's how the overall flow, field behavior, the heat transfer, mass transfer behavior of the system is evaluated. There is a generic equation which is solved. Again, I'll not go into details of it, But yes, every transport equation will have this kind of you know template, or this kind of yeah, it will have this kind of a template, and it will have these different terms within the transport equations. And yes, for every control volume, such equations are solved, and then the overall flow field behavior is evaluated. So this is usually the workflow. We come up with the geometry of the problem which we want to solve. Let's say in this case, it would be some heart model, right? If we are performing the heart modeling simulation, then of course we have to come up with the right kind of geometry. So maybe there might be some modification, maybe some additions, right? So of course we'll see in this coming slides. Meshing is something where we have to discretize the domain into small control volumes, for which the equations will be solved in the solution part, and then with in post processing we are just trying to identify the the way the performance or the different parameters like pressure drop, flow rate, flow velocities, temperatures, those kind of parameters, how they are, and then depending on that. So yeah, that's all about the kind of CFD analysis. What are the steps, what are the workflows. So now coming to our point of discussion, or today's topic of discussion, the heart simulation. So for a in silico heart simulation or its modeling, what all different areas we can look into uh, as an application for this in silico heart modeling. So we do come across these different issues. You can see like the chronic heart failures or heart efficiencies, then chronic heart disease, high blood pressures, right? Or vascular heart disease, attacks, or any birth defects. So when we come across these issues, there are certain surgeries or certain implants which has to be put in place to in order to improve the performance of human organs. So let's say if you look at on the right side, there is a case of some heart inefficiency where you can see how the shape of the heart is being changed because of this particular disease or some inefficiency in the heart. And because of such modifications, maybe now the performance of the heart will modify. The kind of overall flow rate or the overall blood flow it is supposed to deliver, or the overall pumping action it is supposed to perform, or the overall per per minute it is supposed to have, maybe they might not be in place, and then the patient might suffer with some you know other diseases because of this lack of its heart's performance. So in order to first identify this performance, we can use simulation, and then there are certain devices which are developed in order to assist the heart performance, and then again simulation can be used to develop or improve the performance of such systems. So that's what we are going to see in this coming slides. Also, as some other examples where uh, we have some birth defects, and there are certain surgeries which are supposed to be done within a span of period, and those surgeries are related to making a skilled decision. So the surgeon has to make a very skilled decision about how to suture or where to suture these arteries together. So that's all. That's also something we will be looking in the coming slides. When it comes to heart, these areas or the different categories or maybe areas where simulation is already been effective. and been utilized mostly. So some of them could be like placement of the stent, right, in the heart, or near the heart arteries. And this stent placement can have issues like it's not properly aligned in that position, or it might be experiencing some flow pressure, due to which it is experiencing stresses and might fail. Or what is the material we can have, or maybe we can improve the design of that stent, right? These can be the challenges, and simulation can be used to effectively model that stent, that artery, the flow behavior, and then identify the performance of this stent under those conditions. Usually heart is not a steady state system. It's a transient system. It's having blood flow which is a function of time, so it changes with time. So modeling the transient behavior is what will be very effective to know the exact performance of the system or the stent. And again, imagining studies within human body will be very risky, being that as an experimental case will be very risky. And of course, doing it over animals is also something very risky, because of its because humans and animals might have a different behavior as well. So that's where simulation can give that confidence and the idea about the performance of these different systems. So a particular case we'll be discussing would be so whenever we come across modeling a simple heart, it's going to be a complex task because of its complex behavior, or its complex let's say the overall mechanism, I would rather say. So within a heart, actually, we are seeing that there would be expansion and contraction, right? So, and that too is not a actuated by some mechanical device, but it's electrically actuated kind of a mechanism. And beyond that, the different valves within heart, they are also not an active valves, but passive valves. And when we say passive, they actuate or they open depending on the pressure differential. So modeling a case like this where the device is not getting actuated, unlike you can relate it to our normal valves, where we just actuate, or just rotate the valves cock or something like that. It's a knob or something like that, and with we can open or close the valve. But here it is a pressure driven phenomena, where if there is a variation in pressure, only then it will open. So modeling such a situation is a complex phenomena, and there should be a proper strategy to model such cases. And if we look at the different parameters like the pressure or volume, you can see the kind of variation we can observe. On the right side, you can see the variation of pressure with time for a valve, and also the variation of the volume. It is of course it's periodic, but it's complicated. And modeling this component which is having such a behavior would be a tedious task. So let's say even if someone models a heart, okay, simulate it, what would be the output parameters? Like if you recall from the previous slides, we mentioned that there are a couple of output or the detailed informations one can extract from CFD. So then when it comes to heart modeling, what information can be extracted and would be useful for the surgeons or the cardiologists to determine the the performance of this heart. So in this particular slide, you can see that we can extract some pressure versus volume kind of information. Okay, and this information is useful for the cardiologist to determine or to decide whether how is the condition of the heart, and come up with some measures in which they can improve it. So looking at this data about the pressure and the volume, they can decide whether the heart is healthy, or it's performing normally, or is it a abnormal behavior. So this kind of data is something we can extract. So if we try to look at this graph, it's all about the left ventricle of the heart, right, which is supposed to collect the purified or oxygenated blood from the lungs, and then it is supposed to send it to the aortic or the aorta, where it will distribute it to the body, right? So within this left ventricle valve, you can see the different stages of its operation, where in the first stage, the mitral valve is closing off, and the pressure will be increasing, and due to the contraction, and then because of this pressure within the heart's ventricle, and the pressure in the aortic artery being lower than that, the aortic valve will open, right? As I said, this heart valves are passive valves, and they are pressure driven. So when the pressure within this ventricle builds up, the aortic valve opens, and then we go into that stage two, where the volume will start decreasing of this particular valve, and continues, like it's the contraction for stage one, and still while contracting, the valve also opens, and then displaces this fluid, and then the overall volume reduces. After that, again, the aortic valve closes, because now the overall pressure within the ventricle has dropped, and the fluid has been displaced. And in the stage three is where again the pressure will be reduced in the ventricles, and maybe it will also start expanding. Maybe it's now expanding, and then while expanding, because it's expanding, its pressure will go below the pressure of the blood coming from the lungs, and that's where this mitral valve will open, and then we'll have the stage four. So this is again a simple graph about how the pressure and volume of this left ventricle. And with this, if we model this left ventricle or the right ventricle of a heart, and if we try to monitor this pressure and volume of that through the computational tool or the simulation tool, then we can come up with this data and then provide it to the cardiologist, which using which he can determine whether this is a normal behavior, or if there is any abnormal behavior. So this is how the simulation information can be used. So let's see in this coming slides how they. So we understood what is the output we can expect, but then in order to model a heart, as I said, it's a complex system. In order to model the heart, there has to be certain strategy. So the kind of strategy is as follows. A heart model like the one you can see on the screen, where we are modeling the two ventricles, that is the left and the right ventricle. Okay, and you can see we are just modeling the lower portion of it, right? We are not modeling the valves, right? But instead, you can see the portion where the valves are supposed to be there. That portion is being closed off with some lids, right? So there will be two kind of valves, and for the right one, and also two for the left one. One to dispose the fluid into it, and the other to remove the fluid from it, right? So we are not modeling those valves, but instead, what we are doing is we are generating a network. Okay, so this network is nothing but the overall flow network. Okay, across which or against which this heart is supposed to work. So the function of the heart is that is the blood, a non-Newtonian fluid again, whose viscosity will be varying with shear. So to pump that fluid across this network. So within this network, there will be number of resistances. So using some empirical understandings and the kind of experiment database we have, uh, um, the simulation analysts have come this network. Okay, so again, it's a complex network, but from the studies which we have done, we have seen that this kind of a network and this kind of a modeling is very useful to determine the overall behavior of the heart. So what we are doing here is, you can see that the heart will be compressing to a certain volume from the existing volume to a certain volume. Let's say we know this change in the volume. So that change in the volume is nothing but the overall blood which is going to go into this network within 1 beat, right? So when that information is available of the flow rate, we can put up that as a input flow rate for this network, and the overall pressure drop can be identified. So whenever this heart is supposed to drive that particular volume of fluid, like the volume of fluid which is the difference between its expanded position and the contract position. So that fluid is what is going to be our flow rate for the network. And depending on that information, the pressure drop, okay, the overall resistance required to drive this fluid across this network will be evaluated. And that, pressure drop or that resistance is what the heart is supposed to work against. So that's how one can model this particular heart, or let's say this particular study which we are seeing is where this strategy has been used. So you can see in this case, kind of pressure drops we are seeing, one for the left and one for the right. So these pressure informations will be applied on those lids or the closures of these ventricles, and the ventricles contraction and expansion is supposed to work against these pressures, okay, or the delta P's. So this is how, again, a very brief or a generic info about how you can, or how this particular study is modeling the heart with this network in place. Okay. Okay. So with this kind of a strategy, they were able to perform the simulation. So within simulation, right side, they have modeled this particular heart having only the two ventricles, and the upper portion where the valves are present, that portion is being just closed off with some lids. So those lids will be the inlets and outlets depending on the function of the heart. So when it is expanding, of course, the left ventricle, while it's expanding, this lid is supposed to act as an inlet. So the blood should flow into it, and whenever it is contracting, the blood should flow out of it, right? So while having this expansion and contraction, there will be a certain amount of fluid which will be flowing out of it, right? Um, so that in that amount which is going to flow out of it should be the amount which is going to go into the right ventricle. So this is how it should be balanced, because eventually this heart is in a network, and whatever it's a closed network. This our heart and the arteries, it's all a closed network. So whatever comes out from the left ventricle has to go into the right ventricle. So this is how this heart has been modeled in this case, and you can see the results here, where the transparent image you see is the expanded portion, And the colorful image you see here on the right side is the contracted or kind of contracting, somewhere intermediate contracting position. So that's how the simulation will work, where it will move from that um, expanded position to contracted position using some dynamic mesh or some simulation capabilities. And the database, you can see pressure versus volume extracted for these two ventricles, left and right. You can see the overall volume is almost same, right, for either of them, which indicates that there was a good amount of you know balance, like the volume coming from the left is going into right, which is what we are expecting. Or this particular one cycle or one beat is following what we are expecting out of it. Also, you can monitor the pressures developed, okay, within these valves, and those are being plotted in the lower region. So if a particular surgeon or a cardiologist looks at these plots, they can determine from the values of the pressure and the volume whether what is the performance, is it normal, abnormal, okay, or what is exactly happening, okay. One can determine this, and this is how they can come up with diagnosis, okay, for a particular patient, if particular heart has been modeled for that patient. And okay, there was one thing which I wanted to mention. This particular heart is been modeled using some scan data of a patient, right? So some scanned images of the heart of the patient is what is an input for this model, and that's how this particular shape of the heart is being developed. Okay, so the size and the shape, it's a complex shape, right? So again, it's very patient specific. It can vary for different patients. So some who are having some heart disease, maybe they might have a enlarged heart, or maybe a smaller one, depends. And then this overall size will be different. The overall performance will be different, and such graphs which we see might be different. One can determine or utilize the simulation here. Okay. So one might also be interested to know that how how effective are these heart modeling strategies when we compare them to the a real life performance of a heart. So one might be interested to know what is the validation, or let's say where. So that's what, okay, I wanted to also explain in this side. So you can see those very transparent lines, okay, some dotted lines of pressure and volume. The dark lines are the ones which the simulations, and the dotted lines are something which come from some experimental data we collect for the heart. Okay, so again, collecting experimental data for the heart is a challenging task because you have to place the sensors appropriately. So that's where in the next slide I'll be explaining how the experimental information was extracted, and also how this particular heart modeling was utilized for developing a device. We call it as this vascular assisting device. So how this simulation tool or this strategy was utilized for developing that particular device. So yes, these this model, of course, is being validated with some experimental data, and that's how it this strategy was being decided to be taken for the next. So for let's say one of the heart inefficiency could be that it's not beating properly, and maybe it's not developing the right amount of pressure drop, okay, and that's causing less blood flow to go into the network, and maybe you're not having the blood flow in the network. So where this vascular assist device will assist the heart to develop that pressure. Okay, so of course in the next slide we'll see two images of how this particular vascular device is working. But then when someone is designing such device, it is very difficult for someone to first of all design the overall algorithm to control such a device, right? Like the algorithm to control the actuation of this device, right? It should be very synchronous to the heart, first of all. And second, the position of these vascular assisting device. So you can see here there are three such kind of devices which are actuated pneumatically, right, due to air, and they will help the heart to beat normally. Okay, so whenever the heart is not able to provide the right amount of fluid, they will assist it. That's what the purpose of this device is. And this device can also be utilized to collect experimental data, okay, of the pressure across the heart as well. So yes, let's say if we want to understand the performance of this device, use our heart modeling strategy, place those components or that device near the heart. As you can see in this case, we are again modeling the network. We are just in this case, the additional part is that we are just adding this vascular assist device. So this particular study is being conducted by ADCOR from Germany, right? They develop such a device, and they are kind of you know collaborating for this kind of a study. So in this case, just like modeling a simple heart, we are you know coming up with the again the patient specific heart, okay, with the scanned data. We are developing this model. The two ventricles are developed. We have the valves removed, and having the lids. There is a network. Of course, the database of the network is what again patient specific have to be collected appropriately. So once we know that this is how it's going to work, now in this case we have such vascular assist device in place, and we are going to simulate them and try to see that, let's say if this heart is not going to compress effectively, then how these devices are going to help it. Okay, this is how one this simulation is going to go across. So you can see in this particular slide, we are highlighting this case where there are two different positions we are looking at of this heart. Okay, where we are looking at expanded and a contracted position. So we are assuming that this heart it's not able to uh, compress to the expected level by its own, and this assisting device is helping it. And with this data, again we can with the simulation, again we can extract such pressure versus volume data, and then depending on this data, again one can decide upon whether that how to or how much actuation of this device is needed, where is the appropriate position of this device, so as that the normal function of the heart can be extracted as an output, right? um, Maybe positioning the pads appropriately can help to make the function of the heart as normal as possible. Okay, beyond that, this device can also be utilized to collect experimental information, and you can see on the right side the dotted lines is what the experimental information is. And you can see there is a good agreement of course it's not a exact match, but at least the directions are right. And using simulations, you can virtually mimic or virtually have that same behavior and then keep on modifying the device accordingly. So of course this heart is for a animal heart, and that's where they were able to also place such device and extract this information. But yeah, so if you look at the result, we see that there is a good agreement, and this particular strategy can be very effectively used to develop such a device. So that was one type of study, where we are looking at modeling, um, and trying to understand how it can be utilized effectively. There are other areas as well where again simulation can be very effective. Like in this particular case, there are certain cases where a child is born with a birth defect, and that defect could be, like in this case, having a single ventricle. Okay, so if I just read this particular line, it's saying that a long-term prolongedness of a baby is born with single ventricle heart defects can depend on the location of vascular connections. So a particular surgery has to be performed in order to um, modify the network. Okay, in order to avoid the load coming onto this heart. Again, I'll not go into deep or the details of this surgery, but I'll give you the just a brief understanding here. So what this surgery is all about is, it's about detaching a certain network and then attaching, network. Like in this case, if you see, there are two pulmonary arteries, left and right. Okay, and there is a vena cava which is coming from the top side. Okay, maybe I'll use some pointer. Okay, I hope my pointer is visible. So you can see here there are two pulmonary arteries. One is right and left, and there is a superior vena cava which is coming from top. So these are, let's say there are two coming from the top. One would be called as left and right, and the one on coming from the right and the left. These four are supposed to be first, sutured together or connected together. Okay, by removing them from the heart. You can see this super vena has been removed from the right artery, and then it has been directed or maybe connected to this pulmonary artery. So this surgery has been performed to kind of bypass, avoid the flow going into heart and then getting pumped to the lungs, but instead kind of just bypass the flow, to avoid the load coming onto the single ventricle. Okay, so with this particular case, let's say when the surgeon are supposed to decide upon how to connect them. So you can see on the right side there can be number of ways to connect this, because in reality they are not connected, but now we are going to do this modification. So once we do this modification, it should not affect the overall flow behavior, right? There are chances that with this modification, the overall pressure drop might increase, or maybe there might be chances of some recirculating or a vortex region getting generated because of this kind of modification, and that might lead to the overall high pressure getting developed. The whole getting filled because of this high pressure, and the heart has to work against high pressure. So that's where you can see here there are two different options they have come up with, like the way they can connect these. Like the upper two are the supervena cavas, right, left and right, and the lower ones we see are the left and the right pulmonary arteries. Okay, so you can see there are two ways in which they can connect it. So again, this different ways is something the analysts again have a um, a discussion with the cardiologist because they are the experts of this domain. So they come up with this information that okay, we can go with these two kind of strategies. And the third or the next is where they have to also connect the inferior vena cava, okay, with some extra cardiac conduit, okay. So coming up with some extra conduit which is required, they have to again connect this as well to this particular network. So this is again the something we have to add up. So in this way, they have come up with these four options you can see here, four different ways in which this connection can happen. So now looking at this as well, you can identify this is very complex connection, and then the surgeons actually do not go for it at once because of its complexity, and they go for it by just step by step. Like first they go for the first case, and then they add the extra cardiac conduit. Again, the length of the conduit and all is also specific. So if someone has to tell them which one is appropriate, okay, we have four of them, right? They have worked out together and come up with four. Which one is appropriate? That is going to be a difficult task, and that's where until now they were relying on the just the output coming from the patient. Like they were monitoring the patient for a couple of months, and then they used to decide upon which is working. Like they from their experience they suture it, and then give it some time, and then within those months they monitor the behavior, see if it's working, and then go for the next, like adding the content. But with simulation, if we perform simulation, of course the kind of information like the boundary condition, the flow rate, the model itself, you can look at the model is very complex. So these inputs are very complicated, and collect. But once if you are having this, of course, with as I said, due to the advancements, we are able to come up with scan data, and then develop faceted data and come up with such models. We can perform this analysis of the flow, and you can see on the right side the velocity flow streams for these four cases. And then with this information from CFD, one can decide which one is better, right? By looking at the overall pressure drop, or the kind of vortices being generated, or the recirculating zones getting generated. So with this information, one can decide which one is the right, and then with this, the surgeons can go for this, complete surgery in one go, right? They can avoid going it for step by step, but instead they can go with, just one attempt where they can, suture it appropriately. And with this as well, will also have a confidence that the kind of modifications they have put up, um, because of that defect, that modification will last, okay. Because most of the times such patients don't live long because of this modifications. They don't have a very good lifespan. But now with this more information, I would rather say, they get a confidence, and they can properly modify it. So that's how this is again very important, very good study, or a good strategy, I would say. Using an in silico approach, we can properly modify the overall flow across the hearts and arteries. Another area where again simulation is very effectively used is development of stents. So stents are in place to have or avoid the narrowing of these arteries, and then eventually creating a high pressure, and then of course that will also affect the performance of the heart, because it has to work against this high pressure. So developing such stents becomes challenging when the stents are kind of an expanding stents, when they are exposed to such uh, non-Newtonian fluid, there are chances of they getting damaged, right? And then that's the concern of any biomedical or any engineer developing such tents to properly manufacture or understand the performance. So with simulation, with fluid structure interaction, one can identify these scenarios, and you can see in this case, ADMEC and CADFEM together have been solving or analyzing this stent performance using this fluid structure interaction, and they were able to accurately determine the lifespan of this medical device with this multi physics simulation. So this is again another area. So similar to the study, there is this another study you can just change it to arrow. Yeah. So in this particular case, you can also and there was an issue with the fracturing of this nitinol stent frames, right? So using simulation, they were able to identify in what condition this particular stent is working, and then map its stresses. You can see on the right side we are mapping the stresses over that stent, and then wherever the stent is going to have a high stress, the geometry or the material or the overall thickness in that region can be modified, and this stent can be very effectively modeled or prepared for a very patient specific case. Like we can come up with this artery information for that particular patient and then prepare the stent accordingly. And also you can see with this simulation and develop it accordingly, right? So you know identifying this vortices, leakages, the overall stress strains, this will really help any um, you know medical device manufacturer or designer to appropriately design it. Similar study relating to the modeling of the arteries and then trying to understand the overall flow over these arteries. Okay, so again here simulation is helping them to understand particular case whenever there is an expansion of this artery, and then come up with the understanding. Maybe the doctors can decide upon what is the time up to which this kind of uh, this kind of swelling of that artery will be fine, and what is the time at which we should be taking some actions to avoid it. So that's it from my side. So a summary about this overall session we are looking at. So we did understand that yes, heart modeling is possible with, of course, a lot of efforts in overall network. Heart overall heart modeling. If with the testing, yes, we are able to have a very good um, agreement at least where we it can be very effectively used to develop the medical devices for us, so optimizing and developing those devices like vascular assist device or the stents can be performed very well. Yes, this can also help implementations, the cost, time, efforts involved, and also this is so simulation can give you that virtual information, and we can see that the kind of advanced technologies we have, using that we are able to get the realistic um, situation within virtual environment as well. And this information is going to really help surgeons, cardiologists to very effectively take up the right decisions. And I guess, yeah, that's how simulation can be very effectively utilized. Industry leaders who are developing the medical devices. Okay, and you can see that across the globe, you can see, and then across the different categories, you can see how the industry is already utilizing simulation very effectively. Okay, and yeah, so I think that from my side, these are just some